Well, first off, a warm welcome to you all from IonQ. We build application prototypes and quantum computers from ions. These are charged atoms. Thank you also for spending your valuable time to get an update from us on how we're collaborating with Hyundai on applications for the automotive industry. I'm joined here by my colleague, Dr. Sonika Johri, who will share with you some insights on two very interesting projects that we're working on with Hyundai, one in quantum chemistry and one in machine learning. My name is Nicole Barberis. I'm the technical director. Let me move forward here. Yep. I'm the technical director on our go-to-market team, which means that I help clients build use cases and also build partnerships. But I'm also a quantum machine learning developer. So part of the insight I'll share with you today is from that perspective. Now, why are clients gravitating towards IonQ? One is the team of scientists we have and application developers on Sonika's team. In fact, we were listed in the 100 most innovative companies this year. Another reason clients come to us is for the strength of our partnerships. In fact, just a few weeks ago, we announced a partnership with Dell Technologies. And in this partnership, we offer a platform for hybrid quantum and classical computing in which a client on a PowerEdge server can run their quantum simulation on that server, and then when the developer is ready, they can route that program over to IonQ on the cloud and run it on real quantum hardware. So on this slide and the next, I'm going to focus on other reasons that clients are favoring IonQ. One is the quality of our qubits. You heard Dr. Preskill this morning mention how important that is. The second is the vision in our roadmap. So let's start with qubits. We use perfectly quantum qubits, and I mean that literally because we are using ytterbium ions, charged atoms, and they are perfectly identical. In fact, they're fungible. Then about coherence time. Now, from a developer's perspective, coherence time means how much of the quantum effect can I include in my program. Of course, I'm talking about quantum entanglement, superposition, and interference. So this is very, very important from a developer perspective. And we offer some of the longest coherent times from seconds to minutes. Fidelity. This is about, is the computer doing what I'm asking it to do? So when I code in Qiskit or Cirq and I execute that command, is the computer doing what I'm asking it to do? Again, we offer very, very good competitive fidelity rates on our operations, on the gates. Lastly, the spam errors are very low. Of course, spam is not about annoying emails. This is state preparation and measurement. Again, what the takeaway from this slide is that trapped ion computers, right, using perfectly quantum, naturally quantum qubits offer less errors for your application developers. Now, another important reason clients come to us is for our architecture and our roadmap. The unique architecture we offer is all-to-all qubit connectivity. Now, this is very important because as a developer, if I want to entangle qubit 5 to qubit 12, right, I'm able to do that directly. This is because our ions are held in a vacuum with electromagnetic forces. There are no wires, right? So now contrast this to other architectures such as superconducting qubits, where the qubits are hardwired with capacitors and other hardware elements, and the geometry is fixed. Each generation of the geometry, the geometry changes. So as a programmer, I need to keep track of that. That is not an issue with IonQ and our ions in our traps. Now, lastly, modular and scalable. This is critical because we do not use dilution refrigerators. When you see those huge, huge canisters with a human inside, we do not use dilution refrigeration. In fact, our roadmap is pointing us towards smaller, modular, room temperature devices. We expect that you will be able to rack mount these in your data center. Now, ultimately, we are building these quantum computers to run applications for clients, right? To solve problems, real-world problems, eventually, right? Eventually, of course. But how do we measure this progress? At IonQ, we use algorithmic qubits because, as many of you know, counting raw qubits is not at all indicative of application performance. So instead of counting raw qubits, we choose to count algorithmic qubits. This is much more informative for a developer, for a business executive who has to plan an application or fund an application for the next quarter. And furthermore, it's business-centric instead of being engineering-centric, such as quantum volume. Now, I want to give you an example. This is one of our latest systems, IonQ Aria. It offers a qubit, an algorithmic qubit count of 25. And what does that mean? So on the right, you see this graph. And on the y-axis, it tells you how many qubits are available to you as a developer. This means I can size my job. I can size my data structure, right? It immediately gives me information. On the x-axis, you see the gray ends at 512. These are how many two-gate entangling gates that I have available to me as a programmer. Again, at a glance, I can size my job. Now, the colors, the blue means good, close to ideal, and red means noise. And you see here there are a few algorithmic primitives listed, such as phase estimation, QFT. Again, at a glance, as a developer, I can say, wow, this is a good result. Let me start planning out my program. And finally, help me welcome Dr. Sonika Johri, who is going to talk to you about the real-world applications we're collaborating with on Hyundai. And a big thank you to Hyundai. I believe they're in the audience as well. So, Sonika.
Thanks, Nicole. Can I get that? So, hello everyone. I'm Sonika Johri. I lead the quantum applications team at IonQ. And I'm going to dive into some of the technical details of our collaboration with Hyundai. So we're going to talk about quantum chemistry and also computer vision. Let me begin with quantum chemistry. This button. OK, there we go. Quantum chemistry is important in the automotive industry for various applications. So for instance, if you want to design a better battery, you need to understand the chemistry of the molecules inside the battery. Or for instance, if you want to design a better fuel cell, you want to understand the chemistry of the catalyst that is used in the fuel cell. Therefore, Hyundai has chosen, one of the projects that Hyundai has chosen to do with us focuses on quantum chemistry. And for this project, mainly we are focused on solving the electronic structure problem with IonQ quantum computers. And this is a problem which scales exponentially on classical computers. So if you want exact results, practically on classical computers, you cannot actually do much more than 20 electrons. Right? And for the since we are very much focused on what can be demonstrated and understood on quantum computers today and in the next few years, for this collaboration, we've chosen to start investigating investigating a near-term quantum algorithm called the variational quantum eigensolver, which postulates that an approximation to the ground state of physical Hamiltonian can be prepared by using short-depth quantum circuits. In particular, the highlights of VQE, short for variational quantum eigensolver at IonQ, include using the all-to-all connectivity of the qubits, of our qubits, in order to design ansatses which have a lot of non-local correlations. Then also, since we have very high fidelity gates, we can really test very, very deep circuits. And we also focus a lot on using algorithmic innovation to reduce the number of measurements and also the number of parameters in the VQE ansatz, which ultimately leads to the algorithm being run faster and allows it to produce better, more accurate results. Now, on this slide, I've highlighted a few of the algorithmic innovations we've done for this project. So we've, for instance, we've made certain approximations that still give physically meaningful answers, right, but cut the number of qubits in half by using what's called a pair approximation. We've reduced the number of measurements by grouping the terms in the Hamiltonian according to their commutation relationships, so that for each time you measure what's called the cost function in the VQE, you only need 3 circuits versus a number of circuits that scales with the number of qubits. And then we also have proposed and implemented this technique called orbital optimization in conjunction with VQE, which basically, before you perform the VQE algorithm on the quantum computer, you do some classical optimization to find the best set of orbitals on which to perform the VQE algorithm. And then this classical and quantum optimization combined actually gives you extremely good results, which I'll talk about now. So here are results from 2 generations of IonQ's quantum computer, IonQ Harmony and IonQ Aria. And here I show results for lithium hydride and lithium hydride on 3 qubits and water, the water molecule on 6 qubits. Now let's focus, for instance, on the results for the water molecule on the right. So the black, on the x-axis is a parameter that controls the geometry of the molecule, and on the y-axis is the predicted energy of that molecule at that geometry, right? And the black curve is the result from an ideal simulator, right? And in the figure on the right, if you look at the blue points, those are the raw results from the Aria quantum computer of an end-to-end VQE executed on the system, right? So you can see that the Aria results lie above the exact energy curve. So they're not yet giving the precision is not high, or the accuracy is not high enough to give exactly the right answers. However, we notice something extremely interesting, which is that you can shift the blue points by a constant amount at the 2 different geometry parameters, and when you shift them by a constant amount, they fall on the exact on the curve from the ideal simulator, right? So what does this tell you? While we cannot predict the exact energies accurately, we can actually predict the difference in energies accurately, and that is actually what is physically relevant for a lot of applications. For instance, it can allow you that if you get the difference in energies accurately, it can allow you to predict things like reaction rates and so on, right? So even if we can't get the precise answers for the energies, we can get the difference in energies, which is good enough for a lot of practical applications. And then here are also results from studying lithium oxide, which is relevant to battery chemistry on 12 qubits. And here again, these are results from Aria, and here again we see the same effect of once we do this constant shift, we can reach the ideal results within chemical accuracy. And this then constitutes the largest end-to-end VQE that has been demonstrated on a quantum computer without any special error mitigation techniques or without making approximations that make it effectively an uncorrelated system, right? And the results are in this archive paper, and I encourage everybody to go and take a look if you want to know more details. Okay, next, let's talk about computer vision with quantum computers, right? And this is another extremely exciting project we've been doing with Hyundai. So now, for an automated vehicle, right, something that's of fundamental importance is basically being able to precisely tell the location and type of objects that are in the vicinity of the vehicle, right? So for instance, whether there's a pedestrian, whether there's a car, whether there's a truck, and so on. In this field, people use various kinds of data, right? They can use image data, or they can use data from sensors like LiDAR and so on to make this prediction. And we've been working with Hyundai on understanding whether and how quantum computers can impact this object detection. Right? So we're doing various projects with Hyundai on this. Today I'm going to talk about the results of one of them, which is doing image recognition for this German road sign data set, which consists of 43 classes of images of different road signs that are instances of which are shown here. Right? Okay. So for this project, we came up with a quantum learning architecture, right? Which is shown here, right? The quantum circuit here is inspired by a paper on a quantum convolutional neural network, the reference for which is listed at the bottom of the screen, right? We use at the input we use what's called a product state encoding. So basically, we compress the image and then load it into the quantum computer. Right? And there's one data point that's loaded in per qubit. And then at the output of the quantum circuit is fed into a very small classical neural network, which kind of integrates the information from the output and then uses it to make a prediction on the class of the image, right? Since we don't have enough, the number of qubits we have is less than the number of pixels in the image that we have to use some kind of compression to get the data into the quantum computer. And so for this, we used what are called, we tried actually different kinds of compression techniques. We used PCA, but the technique that actually performed the best we found was a variational autoencoder. Right? And we tried different kinds of variational autoencoders and actually found that that a variational autoencoder, which we designed in-house, which preserved the locality of the image, actually worked the best. And at the bottom, you can see some examples of what the performance of the variational autoencoder on various images. Okay, so here are results from IonQ ARIA. Right? So here I'm showing you results from training and results from training the model on the top row on 4 and 8 qubits, and on the bottom row is the performance of the model on a validation data set. So essentially inference, right, after the model is trained on some on the training data set. And you can see that and these are results for 2 categories. So we took 2 road signs and trained the model to make predictions for that. And you can see on the bottom, for instance, on the bottom right image, right, you can reach accuracies of up to 90%, right, on 8, or much more, actually more than 90% on 8 qubits for inference on 2 categories, right? Now, keep in mind that these are not error-mitigated results. These are just results from, raw results from the quantum computer, right? And it's already that powerful, right? You don't need any kind of error correction, any kind of error mitigation. You can already reach these kind of high accuracies with existing technology, right? Now, here we describe the results of a comprehensive study that we did using different numbers of qubits as well as different number of classes, right? And a couple of takeaways from this slide, which actually has a lot of information, are if you go from the curve from going from left to right, that is increasing the number of qubits. The leftmost one is 4 qubits, and the middle one is 8 qubits. The right one is 16 qubits. So as you go from left to right, you actually start increasing the accuracies, right, on the validation data set. Right? And then also, you can see that as the number of categories increases, the accuracies decrease. However, right, as you increase the number of qubits, that fall off in accuracies actually becomes much less significant. Right? And now, armed with this kind of extensive analysis, we can go ahead and kind of make some predictions on, if you had a realistic problem, right? How many qubits would you need to be competitive with classical computers, let's say, right? You can project out to the future, for instance. And then one very interesting thing that came out of this project, right, very, very intriguing, right, is that there seems to be consistently some kind of quantum advantage in the number of parameters that are in the quantum models versus the number of parameters a classical model needs, right? So it seems that very, very compact quantum models can learn the kind of correlations that are, for instance, in this data set, compared to a much larger classical model, right? So for instance, the quantum convolutional circuit we used, right, the largest one at 16 qubits had only 60 parameters, right? Whereas a classical convolutional neural network that had about the same performance needs 59,000 parameters, right? Now, I don't have a complete theoretical framework yet of understanding what the origin of this is, but I think I think this is kind of very intriguing and very promising to look into whether there is some inherent ability in quantum models to be much more effective in describing certain kinds of correlations compared to classical models. And with that, I would also like to spend a minute talking about what's next for Hyundai and IonQ. We're working on various different projects, right? So I talked to you about our project on battery chemistry and also our project on image recognition. So for machine learning, the next thing we're trying to do is object detection, right? So that's a much more complex problem than just image recognition. Object detection is if you're given an image, right, with various objects in it, you have to draw a bounding box around that image, around that object, and then also identify what that object is, right? So we're doing that with Hyundai. We're also doing 3D point cloud analysis, right, which is not just looking at image data, but looking at 3D data that can come in from something like a LiDAR, right? And on the chemistry side, we are looking at metal catalysts for fuel cells, right? And all of these projects are going in an extremely interesting and exciting direction. And I'm excited to share results about these when they come out. And finally, we would like to tell you that IonQ Forte is now available. It has 32 fully connected qubits, right? And we are in the process of using it with certain clients, right? I think that's also going to produce extremely exciting results. Okay, with that, I would like to wrap up, invite people to ask questions, and of course, we love to collaborate. We love to talk about quantum computers, so please come to me or Nicole after the talk if you want to discuss more.